Okay. For the C2 problem of Unit 11 rotato, what we have here is we have more kinematic rotation problems. So these kinematic problems earlier on in the year were stuff like, hey, a car is moving down the road at 10 meters per second, it slams on the gas, and it accelerates at some rate for some time. How fast is it going later, or how far did it go later? We looked at these for the x direction. We then did this for the y direction, like a seagull's dropping stuff onto rocks. And then eventually we did projectile motion here. In these kinematic rotation problems, these ones are a little bit more complicated because we typically have the acceleration. So you'll be using equations 2r, 3r, 4r, and 5r from our best friend sheet. These, if you remember, these have an angular acceleration. And if you watch the video on the C1 problem, we talked about this as well. These are problems specific whenever you have an acceleration there. If your acceleration is 0, you can technically still use these, but they're not really going to give you anything different. Okay, so it's actually easier to use 1r if you don't have an acceleration. For a problem of this, I don't know about you, but we just picked up in my household a Vitamix no, it's not a food processor. It's a Vitamix like blender. I don't know. We make smoothies in it, and they are amazing because you can go to Trader Joe's, get a like bundle or bunch of bananas. Yeah, bunch of bananas for like 19 cents. And you put some bananas, a little bit of yogurt, and some milk, and a smoothie blender, and you go. And then you're drinking a banana smoothie at like 5:30 in the morning, and it's great. Okay, so imagine that you have this smoothie blender, and you can turn it on, and it's kind of moving slow in the beginning. Then you crank that dial up, and now the blade is like got to spin way faster. Okay, so let's pretend we got a measurement, and we said, hey, this smoothie blender initially had a angular velocity, because we're talking about rotations here, had an angular velocity of, I don't know, 100 radians per second, okay? And these things spin up real quick. At a time period of like 0.2 seconds later, it has a final velocity, angular velocity of, I don't know, like 2,000 radians per second. No, let's not make it 2,000. Let's make it 9,000. Wait, where does 0 go? 9,000 radians per second. Okay, let's increase its power level. What we can figure out here is, like, what is the acceleration of this thing? Like, how quickly is it speeding up? To do this, in this case here, if you want to think about this for a second, pause the video, try to figure out which equation you would use. Tick tock, tick tock. What we could use here is if you picked equation either 2r or 3r, you're correct. One of these equations is set up as omega f equals omega I plus alpha t. But if you did the algebra on this equation, you would actually subtract omega I over and then divide by t on each side. And if you did that, you'd find that alpha equals omega f minus omega I over t. And one of those is equation 3r, one of those is equation 2r. They're technically the same equation, but in the end, this is what you're going to have to use. So just by recognizing, hey, just like before, we've got 1, 2, 3 things we can solve for this. We just got to pick the right equation. Picking one of these correct equations here gives us this value, gives us this setup. And now it's just a matter of plugging numbers in and getting something out. Alpha would equal 9,000 radians per second, the final angular velocity, minus 100 radians per second, that initial slow velocity, divided by some time. And we said that the time here was 0.2 seconds. It spins up pretty quick. That's going to give us 8,900 divided by 0.2, so we're like multiplying by 5, gives us 44,000, 500 radians per second squared. And you can remember that that unit is a radian per second squared because just like acceleration is meters per second squared, this is the same ideas, but we just have radians because we're talking about rotations instead of meters. Okay, so we could find alpha doing that. If we wanted to figure out as well, let's just like send the problem even further. If we took all of that rotation that the blender spun and we like unrolled it, like we had that hula hoop in class that was a circle, and I snapped it apart and unrolled it, I stretched it out into a long line. If we unrolled it, we could see like how far it went, but let's just in this case figure out for this blender, what was its angular displacement? Like how many times did it spin around in radians? We can do this once again just looking at our best friend. We actually have so much information here. We could really use nearly any equation we want as long as it has theta in it. Because we have initial angular velocity, the final angular velocity, the time, and we just solved for the acceleration. So we have nearly everything. Just choose an equation that you'd like to use that has theta in it and plug everything in and collect your answer. I'll use the equation that matches up with the 1/2 at squared. I could say that theta equals the initial angular velocity times time plus 1/2 alpha t squared. And if I just plug things into this equation here, let's see, our initial angular velocity was 100 rads per second times 0.2 seconds plus 1/2 times this huge number we found for alpha, 44500 rad per second squared times 0.2 seconds squared. Now it's just a matter of, crunching numbers. 0.2 times 100 is 20 radians, and then plus, 0.2 squared times, well, let's just do this in steps. 0.2 squared is 0.04 naturally. I'll divide that by 2 to get 0.02. I'll multiply that by 44,500 and get 890 radians. Put them together, and what do you got? 910 radians. Okay, so that's how far angularly this object has rotated. If we wanted to put this in terms of pi, we could just multiply and divide it by pi. If we divide by pi here, 910 divided by pi is going to give us 200 and about 90 pi radians. Those are equivalent answers. They're the same thing. They mean the same thing. They're just talking about in terms of pi or not terms of pi. I like talking about things in terms of pi because if I divide this 290 by 2, it gives us how many revolutions we've gone through, because every 2 pi radians is a revolution. So approximately this blade has spun 145 times in 0.2 seconds, which is kind of a cool thing because that's half of 290. So, if you wanted to do that conversion, you can say that 1 rev is 2 pi radian. Cancels out the radian, get rid of the pi, divide by 2, you get 140 rev. So either way you want to slice this, it's fine. Honestly, if you just put 910 as your answer, I'd accept it. If you wanted to put the 290 as your answer, I'd accept it. If you wanted to put 140 rev, I'd have to figure out what you did for a second, but I'd accept it too. They're all correct answers. Okay? So for these C2 kinematic problems, you're still just using what we did all the way back to the beginning of the year. You are checking out what variables you're looking at and what you're trying to solve for. You are picking the proper equation. You're simply writing that equation out with everything in it, and then you're playing the solving games. Once again, for the second part here, we figured out an equation we could use. We plugged everything in, and then we got an answer. If you want that answer in different setups, that's fine as well. Okay. With that though, this problem is finished.